Hi everyone, it's Linnea Tucker. I want to quickly go over definition of perfect squares and square roots and how it all works. All right, let's talk about perfect squares. If I take a number and raise it to the second power, that means I'm taking that base of 1 and multiplying it by itself twice, and I get 1. It does not mean I'm taking 1 times 2. That's not the definition of a power. You're taking your base of 2 and multiplying it by itself twice, and 2 times 2 is 4. 3 times 3, this says take 3 and multiply it by itself twice. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25, and so on. Okay? 10 times 10 is 100. All of these numbers are called perfect squares. Okay, and I'll show you on the next slide the reason I think it was given the name squares. Okay, so perfect squares have 2 equal integer factors. Another definition is any number that can be written as an integer to the power of 2 is called a perfect square. All right, so there's 2 definitions of what a perfect square is. Okay, if you wanted to model a perfect square, your base here is the side length of a square, like this, and the answer is the area of the square. Okay, so if I have a square with a side length of 1 by 1, well, area is length times width. 1 times 1 is 1. It has an area of 1. Here, my base is 2, so that means my side length is 2. 1, 2, 1, 2. A square with a side length of 2 has an area of 4. See how that works? A square with a side length of 5, 1, 2, 3, 4, 5, by 1, 2, 3, 4, 5, has an area of what? Yeah, it has an area of 25. Okay? So I think that's why they call them perfect squares. All right. Now, if you can do something to a number, you can always undo it. If you can take a number and add to make a bigger number, then you can turn around and subtract to get back to your original. Addition and subtraction are inverse operations. If you can take a number and multiply by another number to get a bigger number, then you can undo that operation with division. Well, perfect squares and square roots are inverse operations also. One undoes the other. Okay, so we've talked about perfect squares. All right, what if we start with our perfect square and we want to get back to the original number, our original base, or some people call it the root. Here's my original number, which is the base on the exponent. That's called the root. So if I give you the answer, like the area of 25, and I put it under this square root sign, this radical sign, what it's asking you is what number times itself gives you 25. Well, you can rewrite 25 as 5 times 5, so let me ask you again. What number times itself gives you 25? Yeah, the answer is 5. What number times itself gives you 16? Well, you can see right there it's going to be 4. So what you're doing with a square root, your answer for a square root is the base on your original exponent. Do you see that? Now, the mistake some people make when they take a square root is they write the answer like this. And that's not correct, because this is in exponent form, but in expanded form, that's 16, and the square root of 16 is not 16, and the square root of 25 is not 25. So don't square your answer. That's not what we're looking for. We're looking for the original base. Okay? Square root of 9 means what number times itself gives you 9? Well, that's 3. Square root of 4, what number times itself gives you 4? Yep, that's 2. And then we've got 1. So a square root, here's a definition, a number that produces a specified quantity when multiplied by itself. Okay? All right. I've already shown you this. A square with a side length of 4 produces an area of 16. What if I start off and I give you an area of 16? I say, okay, the area of a square is 16. What's the side length? Well, you know it's a square. So to get back to the side length or the root, you just take the square root. And the same here. Remember, this one has a side length of 5. 5 times 5 gives you an area of 25. What if I give you the area and ask for the side length? Yeah, you just have to undo the operation. So it's working backwards. All right. Here's another thing I wanted to show you. This is going to help us in CPM4 Module 2. Another way to look at these square roots is, remember originally I took the base of 2 and squared it? Okay, my pen is locked up here. I think my pen just ran out of juice. That's okay, we can do without it. All right, originally I took 2 and squared it and got 4. Well, if I take the 4 and leave it in exponent form as 2 squared, there's an index here, and for a square root it's invisible, but the implied index is 2. So taking the square root of something that's been squared, this cancels out with this, leaving you just the 2. Do you see that? The index here is 2. Taking the square root of something that's been squared, they cancel each other out and you're left with the 3. The square root of 4 squared leaves you 4, and a square root of 5 squared leaves you 5. Just another way of looking at it. Okay, numbers actually have 2 square roots. I just showed you that the square root of 4 is 2, because 2 times 2 gives you 4, but there's actually another square root for 4. Can you think of what that might be? Yeah, it's -2, because -2 times -2 also gives you +4. Take a look at this one. If I take 9, take the square root, I get 3, but there's another answer. The other answer is -3, because -3 times -3 also gives you +9. Okay? We call the positive square root the principal square root, and the other answer is called the negative square root. So how do you know which one they're asking for? Well, in math, all mathematicians agree that if we want the negative square root, we're going to put a negative sign out front. Okay? Basically what this says is take the square root of 4 and now make it negative. Take the square root of 9 and now make it negative. If you don't see the negative sign out front of the radical sign, then you're looking for the positive square root. Okay, I know that you might have a question about, okay, we went from the square root of 4 and we jumped to the square root of 9. What about all the other square roots in between? Like the square root of 5. Well, can you think of any integer times itself that gives you 5? No, because 2 times 2 is 4 and 3 times 3 is 9. So the square root of 5 has to be a number between 2 and 3. This is where you've got to grab a calculator and run it through the machine, because I don't know any number times itself. I don't know any integer number times itself that gives you 5. If you take the square root of 5 in your calculator, you get this really long decimal. And the same with the square root of 6, 7, and 8. But you can tell that the number's getting closer and closer to 3. Here I've got 2.2 if I rounded the tenths place. 2.4 if I round to the tenths place, 2.6 if I round to the tenths place, and 2.8 if I round to the tenths place. It's getting closer and closer to 3. But take a look at all of the decimals. All of these decimals, the 3 dots at the end, indicates that it goes on forever. These kind of numbers never terminate and they never repeat. Okay, so we've got our 2 perfect squares. All of these other numbers are called irrational numbers. All of these decimals that never terminate and never repeat, they're irrational. They never terminate and they never repeat. A perfect square is a rational number, meaning you can turn that number into the ratio of 2 other numbers. For instance, like 2 over 1. 2 divided by 1 gives you 2. 3 is a rational number because you can change 3 into the ratio of what 2 numbers? Yeah, 3 divided by 1. All of these irrational numbers, you cannot do that with. There is no way to change these numbers into the ratio of 2 integers. All right? So we've got rational numbers and irrational numbers. So here's a perfect square and square root chart. Might be handy to put that in your notes. That's all I have to say on this for now. There will be more coming.